Good evening, sir.
Yes, good evening. Yes, today part is coordination now.
Yes, sir.
Last time we have discussed topic. Geometry distortion, yes, no?
Yes, sir.
Today, color and electronic spectrum.
Yes.
Let me start. Basic introduce yourself. Then we will discuss.
So my name is Avantika. I belong to Hisar. I have completed my matriculation and 12th from Holy Angel School, Hisar. And I have done my BSc-MSc dual degree course in chemistry honors from Guru Jambheshwar University of Science and Technology, Hisar, which is in Haryana.
Yes, good. Color and electronic charge transfer spectra. Yes. Why transition elements show in colored? Explain.
Sir, the basic phenomena behind color is that the color which is absorbed is different from the color which is being seen. It's of a particular when visible light of particular wavelength, like if uh, um, like if uh, if blue color is absorbed, then we will see orange color because the absorbed color is not seen. If the all the in sunlight all the 7 colors are present, and if all the colors are absorbed, then black color is visible, and if all the colors are not absorbed, then we can see white color. And the there occurs the transitions also, like DD transitions and charge transfer occur through which we can see color. And if the wavelength of light which is absorbed, then the color that is corresponding to that frequency or wavelength is seen.
Yes, what is DD transfer? What the difference between DD and charge transfer? Which compound is so DD and charge transfer spectra? Explain. And why?
Sir, in a DD transition, like if the d orbitals are split in octahedral complex in T2G and EG, if there is a vacant position present in EG orbital and filled in T2G orbital, so that transition can occur in another d orbital that is known as DD transition. And in charge transfer spectra, the electron is there are no like like MnO4 negative is then in MnO4 negative, Mn is in plus, Mn will show +7 oxidation state, which ag- that shows that it has D0 configuration. So here the oxide ion that is which is associated with manganese, that is in MnO4 negative, which will transfer its electrons to it. This is known as charge transfer transition. So in charge transfer transition, this is the phenomenon showing color.
What is magnetic moment? What the formula of magnetic moment? How to determine any magnetic moment in any compounds? What the procedure?
Sir, magnetic moment, the formula of magnetic moment is under root of n into n plus 2, where n is a number of unpaired electrons, and the magnetic moment is represented in Bohr magneton unit. And in a magnetic moment, we can define it as the magnetic like the if we put like if it shows some in magnetic field, if it comes parallel to the lines come like there are ferromagnetic and paramagnetic and diamagnetic substances. Like in diamagnetic substances, the lines cancel each other, so it has a
Yes, I explain on board. Yes, whiteboard. Yes. Yes.
sir magnetic moment.
Yes. Magnetic moment. Yes. But the formula, how to determine, suppose D1 complex. How to determine D1?
D1.
D1 complex, any D1 complex. Titanium H2 का whole 6 2 positive, 3 positive. वर्टिकल वर्टिकल इसको थोड़ा चेंज कीजिए. Yes. Yes, right.
Magnetic moment is denoted by mu, and its formula is under root of n into n plus 2. If we have to find magnetic moment of Ti H2O3 positive, then its configuration is D1. So Here only one unpaired electron is present.
Yes.
So its magnetic moment will be around 1.8.
Yes. Next, what is orbital diagram? Explain.
Sir, orbital diagrams are correlation diagrams, and it is a hypothetical theoretical diagram, not spectra. And in orbital diagrams, we show relation in uh, energy of terms and field strength. Orbital diagrams are used for weak field ligands, which weak field ligands, and orbital diagrams explain spin or for orbital diagrams can be used for weak field ligands that are spin allowed, and weak field ligands have a high spin. In a correlation diagram, the in we on a y-axis we show energy of terms, and in x-axis we represent field strength, and we represent ground state term and excited state term. The excited state term should have the same spin multiplicity which ground state term have, and it can't be used for D5 high spin because it is not a spin allowed transition. For example, if we have taken a D term, then if it will split into T2G and EG, and in that orbital diagram, if one DD transition is possible, then if we draw electronic spectra, then we can represent it at like a peak. That one peak will denote the number of DD transition or charge transfer spectra. And if the transitions occur like if two types of transitions occur, basically electron transitions or hole transition. If there is more chance, like if we have a D1 electronic configuration, then in T2G orbitals below, we have one electron, and in EG orbital above, we don't have any electron. So the T2G orbital, which is having one electron, will transit to the EG orbital, and the vacant EG orbital is having where no electron was present is that is hole is present, then the hole will transit to the T2G orbital. And if there are we can take example of hole transition also, like in D9 electronic configuration, we have 6 T2G filled orbitals, and we have 3 EG 3 electrons in EG orbitals. So there is only one hole present in EG orbital. So here whole transition will occur if like from EG orbital to T2G orbital. If the electrons are more than hole, then hole transition will occur. And if holes are more than electron, then electron transition will occur. If electrons and holes are equal in any electronic configuration, then electronic transition will occur.
Yes, explain on board. Even D2, D3 examples. Oh, and what is the difference between tetrahedral and octahedral orbital diagrams?
So orbital orbital diagrams are made between like here we will represent the ground state term. Here we will represent excited state term. This excited state term will have same spin multiplicity as the ground state term. And if we are splitting here the D term, from T2G to EG, then here only if one DD transition is here occurring here, then if we draw electronic spectra, so in electronic spectra we represent intensity or number of transitions and wavelength or wave number. So here in electronic spectra we can represent number of DD transitions. We have D9 electronic configuration. Here one hole is present. So here one whole transition will occur. And if we have here one electron is present, so here one electron transition will occur. And sir, I have to make organelle diagram of
Yes, what the difference between organelle diagram and Thevenot-Sugano diagram? What the difference?
sir, organelle diagrams are used only for weak field ligands which are spin allowed, but the Tunabo-Sunabo diagram is can be used for weak and strong field ligands. The Tunabo-Sunabo diagram explains spin allowed in spin allowed transitions in high spin complexes having D1 to D9 electronic configuration and spin allowed in low spin complexes having D4 to D7 electronic configuration. It in a organelle diagram we can't explain the D5 high spin which is spin forbidden, but with the help of Tunabo diagram we can also draw the spin forbidden in high spin complexes.
Yes. What is a nephrostotic series? What are the uses of these ones? Color and electronic spectrum.
Sir, there are two parameters. Raka parameters which are denoted by B and C. B and C, the Raka parameters are empirical integers which determine the energy gap between two spectroscopic terms due to electron repulsion. So the energy gap between two spectroscopic terms of same spin multiplicity is measured in terms of only B. So the if there is same spin multiplicity, then the energy gap between two spectroscopic terms is measured in terms of only B. And if there is different spin multiplicity, then the energy gap between two spectroscopic terms is measured in terms of both B and C. Or in the complexes, the value of Raka parameters become less than that of free metal ion. For example, if there is a complex of chromium, Cr H2O6 3 positive, let us take, then there is, and also we take a free metal ion, that is chromium plus 3, and chromium plus 3 have a D3 electronic configuration, and if we represent the electron repulsion in complexes and metal ion, then in then in case of that complex, electron get delocalized with the ligand covalent bond. So in case of complex, there is less in case of complex, that in the complex the we can represent it by beta dash, and the metal ion can be represented by beta. Then in case of complex ion, there is more in case of free metal ion, there is more electronic repulsion than the case of complex. So the uh, the reason of less the reason of less electron repulsion in case of complex is because of that delocalization of electron. So that decrease in value of B due to delocalization of metal electron is called a nephloxitic effect. The nephloxitic parameter is denoted by beta, and we can find this beta by beta of complex ion by B complex, which is divided by B metal ion, and we have denoted the B complex ion by B dash and B metal ion by B. So the lesser the value of B dash, lesser is the electron repulsion, and the lesser the electron repulsion, the higher will be the covalent character. So we can say that beta is directly proportional to B dash, and B dash is inversely proportional to covalent character.
Yes, good. What is charge transfer spectra? How many types of charge transfer spectra? Yes.
Sir, charge transfer spectra in charge transfer spectra, charge transfer occurs like uh, uh, if there is ligand to metal charge transfer, that is LMCT, then for LMCT to occur, there should be the ligand should have a more electron donating tendency. The ligand should have a lone pair, and the metal should be in high oxidation state, so that the metal can acquire have tendency to acquire the electron from ligand. So here ligand to metal charge transfer occur when metal is in high oxidation state, and there is another charge transfer spectra, that is um, metal to ligand charge transfer. In metal to ligand charge transfer, the metal is in low oxidation state, and uh, metal is in low oxidation state, and the it will donate to the ligand, and there is another charge transfer spectra, that is intra-ligand charge transfer. In intra-ligand charge transfer, uh, the transfer the transfer occurs in lig uh, intra-ligand. For example, in case of heme in case of heme group in hemoglobin, the that is an example of intraligand charge transfer, and
Yes, charge transfer is five types, no? Ligand to metal charge transfer, metal to ligand charge transfer, intervalence charge transfer, intravalence
yes,
charge ligand charge transfer, metal to metal charge
yes,
transfer. Yes, no?
yes.
My question is example of all five, one by one.
Uh, like in RU4 O4 negative is an example of MLCT. Hemoglobin and chlorophyll is an example of intraligand, and
Any limitation of Tegane-Segano diagram and organ diagram in coordination? Any limitation?
sir, organ diagram are hypothetical theoretical diagram, and it can't be used for D5 high spin complexes. Organ diagrams can't be used for spin forbidden transition, and the spin multiplicity
Yes, you use term of spin multiplicity. Yes, spin multiplicity, transition allowed, forbidden, intense color. What the meaning of these terms?
sir, uh, the spin allowed can be explain as if spin of an electron is clockwise, then the transition the transition to which orbital is occurring, then the in that orbital the spin should also be same, that is clockwise. And if that is same spin, if both are clockwise, then we say that the transition is spin allowed transition. And in spin forbidden transition, if the spin of an electron is clockwise, and if we have to it have to do transition to the orbital which already has clockwise if it already has one electron of clockwise spin, then that then that same then that clockwise spin electron will not be the transition of that will not be possible to that orbital, because in one orbital two different spins are possible, clockwise and anti-clockwise. With clock, so that it doesn't violate the Pauli exclusion principle.
Yes. What the difference between transition colored spectra and lanthanide actinide colored spectra? What the difference? And what the measurement and what is the procedure for measurement color in chart transfer?
So in case of transition elements, we measure we can directly measure in case of transition elements for like if like the and we can also directly measure the magnetic moment in a case of transition elements, but in case of lanthanoids we have to find the J value, and in and uh, the color transition, like there in case of F in lanthanides in case of lanthanoid complexes the
Yes, no problem, कोई बात नहीं. Yes. नेक्स्ट हम डिस्कस करेंगे जो पार्ट बचा है इसका कलर का, इसको डिस्कस करेंगे. और मैग्नेटिज्म, यस, गुड है, एक्सप्लेन. थोड़ा और डिस्कस करेंगे इसमें, है ना. कुछ चीज़ें जो हैं वो लिमिटेशंस वगैरह आप थोड़ा डिटरमाइन कीजिए और उनको थोड़ा स्टडी कीजिए. यस.
ओके सर.
ना, बाकी ठीक है. मैग्नेटिज्म और लास्ट का जो नेक्स्ट कोशिश करेंगे कल हो जाए कंप्लीट.
Magnetism and charge transfer.
मैग्नेटिज्म में रिएक्शन मैकेनिज्म